properties such as their masses and their velocity dispersion. And in particular, here we see that more massive galaxies host more massive black holes. And I find this correlation particularly remarkable because we need to think that galaxies and supermassive black holes have several order of magnitudes in difference in their physical scale. But however, it looks like they somehow know about each other. And the other piece of evidence is shown on the right. So let's observe now the growth history of galaxies and black holes across cosmic time. So we see in yellow the star formation across the history of the universe, and in blue the black hole accretion. And we can notice that the two lines have a similar trend, and in particular there is an increase to an age of the universe of 3-4 gigayears. So this is the so-called cosmic noon, when both growth histories had their peak. And this is particularly relevant, and it's also the main focus of the talk later on, because the energy emitted by the supermassive black holes is at its maximum. So it may have the strongest impact in the history of the universe. And so somehow we see that the two quantities co-evolve together. So the collection of the effects that the AGN having in regulating the star formation activity of the host galaxy is the so-called AGN feedback. And one of the mechanisms through which AGN feedback can regulate the growth of the galaxy is outflows. And these are I'm going to tackle it from an observational point of view because I'm an observer, and this is actually a big challenge because outflows are a multi-scale and multi-phase phenomenon, as we are going to see in a moment. So winds are launched from the disk surrounding the accreting supermassive black hole on sub-parsec scale, and so this is the image at the top left, and we observe this kind of winds mainly at high energies in X-rays through highly ionized disk winds. And moving on larger physical scales, so parsec, kiloparsec scale within the galaxy, we can observe cold molecular gas winds, for example, in the submillimeter and radio, and they are often identified through these asymmetric and broad features in the emission line. And then moving on even larger physical scales, so tens of kiloparsec, winds can be observed through in the ionized phase, in the optical and near infrared. And you see here a very nice example of a nearby galaxy where the galaxy disk is observed in red with the H-alpha line, so color-coded in red. And then with the oxygen tree, we see in green this biconical structure, which is tracing the outflow. So the take-home message here is that outflow so far have been observed at different cosmic epochs in different types of galaxies. They are quite ubiquitous in the universe, but what we miss is the observational evidence that outflows are able to regulate star formation in the host. And so I would like to introduce a possible way to look for AGN feedback effects, which is also what I'm going to discuss in a moment. So let's consider this cartoon with an outflow propagating to the galaxy and sweeping the cold gas reservoir away. And then on the one hand, we can characterize the feedback mechanism itself, so look at outflow properties. And on the other hand, we can study the properties. We can study the properties of the galaxies that are impacted by feedback. And in particular, here we can look at the star formation activity and the cold gas content. And I refer to the cold gas because this is the direct fuel for star formation. And so in terms of tracers, we can consider the ionized gas phase for outflows and look at the oxygen 3 line and carbon 4. And for star formation activity and cold gas, respectively, we can consider the far infrared luminosity as a tracer for star formation, so emitted by dust heated by star formation. And then one of the most popular tracers for cold gas is the carbon monoxide or CO molecule observed in the submillimeter. And so basically these are the ingredients that we'll see in the rest of the talk. But before starting to show you some results, I wanted to spend a moment to discuss a very interesting perspective that we have started gaining in the last couple of decades through integral field spectroscopy. So first of all, I told you that oxygen-3 is a very popular tracer of, well, ionized gas, but outflows as well. And why this is the case? Well, oxygen-3 is a forbidden line. Therefore, to be produced, it requires low densities, which can be found in the so-called narrow line region, which is the one highlighted in light blue here. So the narrow line region is kiloparsec scale distance from the supermassive black hole. And therefore is less affected. Let's say if we identify broad and often blue shifted features in the emission line, as you see here in the blue box in the spectrum, then these features cannot be produced by the fast gravitationally bound motion of the gas, which instead happens in the broad line region, which is highlighted here in green. So much closer to the supermassive black hole, and where, if we identify broad components in the line, in this case, they are due to the they can be due to the fast motion of the gas around the supermassive black hole. And so this is the reason why for oxygen-3, but also other forbidden lines, these broad and blue shifted components in the line are often used to trace outflows. But then, on top of the spectral information, with integral field spectroscopy, we also have the spatial information. So as you see here, we have the two spatial axes, and the third axis is the wavelength. This means that we can, for example, integrate the emission from the blue box, so this blue shifted and broad component, and then look at the distribution of the outflow in the galaxies. You see in this example of a high redshift, redshift 2, around 2, if I remember correctly, where in white you see the contours of the outflow, so we can map its kind of projected distribution in the galaxy, and we can compare this, if we have enough data, with the distribution of the star formation in the galaxy. And in this particular example, they found an inter-correlation between the distribution of the outflow and the star formation. And this was considered as an example for the instantaneous shutdown of star formation in the galaxy. Although these kind of observations are very difficult, and we'll discuss them more in the rest of the talk, but the main take-home message here is that we need this kind of observations to probe the extension and the morphology of the outflow, so to have a full view on this phenomenon. And so what kind of strategy we adopted by using integral field spectroscopy observations? Well, in this plot, you see a collection of observations of AGN with oxygen-3 traced by IFS data. And on the y-axis, there is the bolometric luminosity of the AGN as a function of redshift. And what you can see is that in the local universe, the coverage in AGN luminosity is quite uniform, and this is what we want if we want to probe kind of the full extent of the AGN population. However, when we move to higher redshift, what we see if we focus on the black points is that these observations are quite biased because they are focused on targets with high luminosities. And in some cases, for example, the target was already known to host an outflow. And so there are now two complementary surveys that are trying to tackle this problem. And these are SUPER in red and CACH-Z in blue. So they are both IFS surveys. Super in particular covers a wide range in AGN luminosity, as you can see here, with high resolution observations, but the sample is representative but not very large. And then CASH-Z it covers a much more statistical sample, but with lower resolution observations, and also covers a wider redshift range. So I will start with Super, since it's the survey I've been involved with in the last few years. This stands for SINFONI Survey for Unveiling the Physics and Effects of Radiative Feedback. It started as a SINFONI large program, so the VLT. Well, SINFONI is not an active instrument anymore, but it used adaptive optics, so this is why we have higher resolution observations. And in particular, it's a blind survey, so we try to be unbiased, meaning that we didn't pre-select for the presence of outflows in our targets. We just selected around 30 AGN at cosmic noon based on their X-ray emission, which is one of the most used proxy for AGN activity. We selected targets from fields of the sky with great multivalent coverage, and in case you are familiar with them, you can see them highlighted in this map, for example, Cosmos and CDFS. And if you want more details for the characterization of the properties of the sample, you can check our survey paper in 2018. And the data we had available, is H-band observations to cover the oxygen 3 line, and then K-band to cover H-alpha as a potential tracer for star formation. In terms of spatial resolution, you see here a bit better what I was saying before. So this is the same plot I showed in the previous slide, but in this case, we have on the y-axis the spatial resolution of the observations. And so you see that with Super, we try to kind of obtain a representative sample of observations with the highest, among the highest resolution possible. So let's start with the characterization of the outflow properties, and we have now the ionized view because we are focusing on the ionized phase of the gas. For this work, which is a combination of results for this, let's say plots, it's a combination of results from CACAD 2020 and Vietri et al. 2020. We combined observations from SINFONI, tracing the oxygen 3 line, and you see here an example of the spectrum with H beta and the two oxygen 3 line, and then the outflow maps. So on the left here, you see basically a map of the velocity of the outflow, and then a map of W80, which is the traces, the full Widal maximum of the line. And what you see is that in the areas where the line is broadest, it's also the outflow is also the kind of fastest, the highest velocities. Then we combine this data with publicly available SDSS spectra tracing the carbon 4 line, and you see here at the bottom one example. So what we could do with this data was to combine observations from the broadline region and the narrowline region, tracing outflow from parsec to kiloparsec scales. And what we observed is the following. So we detected outflows in all the targets analyzed, and this is just half of the sample, covering the AGN, which are unobscured or type 1. So this is why we could see such a kind of broad emission in the SDSS spectra. We found spatially resolved emission for 35% of the sample, with outflows extended up to 6 kiloparsecs. We observed also a correlation, as you can see in this plot at the bottom, between outflow velocities from parsec scale, so in the broadline region, and kiloparsec scales from the narrowline region, meaning that the winds in the broadline region are able somehow to affect the kinematics in the on larger physical scales. And then the other result I wanted to highlight is that we found the more powerful AGN, you see here on the x-axis, the AGN luminosity, host faster and more massive outflows. as you see here, with the increase of the mass outflow rate as a function of AGN luminosity in both the broadline region and the narrowline region. So here we observe a different normalization of the scaling relations, which may be due to different coupling mechanisms of the winds with the interstellar medium, due, for example, to density and temperature of the gas. So now we've seen how to characterize the outflow properties, and let's have a look at their impact on star formation. So let's start with the dusty view of the problem, and I say dusty view here because we used the dust continuum as a tracer for star formation. In particular, for a small subsample of AGN, we obtained ALMA observations with a similar resolution as what we had available from SINFONI. And therefore, we could compare the distribution of the dust and the distribution of the outflow in these galaxies. And this is a work led by Isabella Lamperti. So here on the left, you can see in the foreground in white the distribution of the dust. And in the background, in the color-coded map, you can see the distribution of the outflow obtained by collapsing the blue channels in the spectra. And what we found for this AGN is that there is no clear anti-correlation between the outflow distribution and star formation, meaning that where there is the outflow, there is also dust emission and so star formation. So it's not necessarily true that there is no impact. It could be that, for example, it happens on smaller physical scales than what we are probing here with our observations. Or it could be a matter of time scale, because outflows need more time to affect star formation, and therefore the effect is not instantaneous. So what can we do at this point? We can turn our attention to the cold gas content, because any effect of the AGN will have an impact on the gas reservoir first, and then on star formation as a consequence. So let's start with the idea that AGN feedback may play a role in affecting the gas reservoir of the host galaxies. And then let's ask ourselves this question: do AGN show a different gas content compared to a comparison sample of inactive or non-AGN galaxies? So if we look at the literature, we find the following results. In the low redshift regime, the answer seems to be no. So for different works, they didn't find a significant difference between the two populations. And you see here an example by Usman and collaborators, where they show this basically the integrated Schmidt-Kennicutt relation. And you see, so star formation rate, sorry, is a function of molecular gas mass. And you see that the two populations occupy the same area of the parameter space. But then if we go at higher redshift, so the redshift higher than 1, the answer seems to be more difficult, more contradictory. And although some works found the AGN show lower CO luminosities or molecular gas masses as a function of far-infrared luminosities. The problem at high redshift, however, is that the studies are normally focused on a few often bright targets, or on to collect more samples, they focus on literature collections. And this means that when we put together results from different observations, different samples, we end up with different transitions of the CO molecule. So this is the CO ladder with the different energy levels emitted of the lines emitted by the CO molecule. And to have everything comparable, then we need to convert the different observations to the same ground level, normally the 1 to 0. And to do this, we need to assume conversion factors quite often unknown, and therefore this injects further biases in our analysis. So this is what we try to tackle with SUPER. In particular, we obtained follow-up ALMA observations for a fraction of the sample, and we looked at the CO 3 to 2 line. The sample was made of a 27 AGN with 1 arcsecond resolution, so basically integrated emission. And you can see one example on the right, where there is the flux map at the top and the spectrum at the bottom. So this represents the first systematic study of the molecular gas content of AGN at this redshift, with the additional goal of also minimizing assumptions on conversion factors. This means that we selected our comparison sample of inactive galaxies from the literature, but we matched targets in redshift, stellar mass, star formation rate, and in particular, these are a very important point, we consider targets observed in the same CO transition as our AGN sample, just to avoid the unknown conversion factors that I mentioned earlier. And in this plot, you can see the distribution of the two populations on the main sequence of star-forming galaxies, so star formation rate as a function of stellar mass. And you see that in terms of AGN luminosities, we cover around 2 orders of magnitude, so trying to kind of include also less luminous targets. And before showing you the results that we obtain here, I wanted to complement this sample with an ongoing work that is being led by Elena Bertola, former PhD student in Bologna, now a postdoc in Florence. So she complemented the super sample with the CASH-Z survey that I mentioned earlier on. And so this is still an IFS survey with CHEMOS, another instrument at the VLT. And what she did was to mine the ALMA archive to look for CO observations of these targets. She found CO221 and CO322 observations and collected a sample of around 40 AGN, a bit more heterogeneous in terms of resolutions, of course, and also the lines observed, and covering as well a larger redshift range. So the goal here was to perform an archival study of the molecular gas content of AGN with the aim also of increasing the amount of lower luminosities or more regular AGN. And you see this point in this plot, where CASH-Z in blue is covering, apart from a larger redshift range, also lower luminosity, bolometric luminosities of the AGN. And here the comparison sample was selected the same way as the previous, the super work. Okay, so let's take a look at what we observed for these AGN samples. So I'm going to show you the comparison between the molecular gas reservoir, which is traced by, I use here the CO luminosity as a proxy, as a function of star formation rate, traced here by the far-infrared luminosity, and then as a function of stellar mass. So basically we'll be looking at gas fraction, so the ratio between molecular gas mass and stellar mass. So for the super sample, this is what we see. Well, the first, probably one of the things you may notice is that there are many little arrows in this plot, meaning that we have many upper limits. We need to include them in our analysis, and to do this and so be able to implement priors, obtain posterior distributions, and so on, we implemented a Bayesian framework for our analysis. And then what you can see is that for a given star formation rate, AGN in red show lower CO luminosities, but also their gas fractions are overall lower. So let's focus here on the field histograms, which show you the posterior distribution of the mean of the whole population, of the mean gas fraction of the population. And then the data points here represent the observed data we have. So here the difference is significant at the 2-3 sigma, so it's still a small difference. But then when we include in the sample also more lower luminosity AGN, we notice here that the differences start to disappear basically as a function of star formation rate, although in the gas fraction parameter we still see some difference. So what we are concluding here, since the work is in preparation, is that basically the difference between the two populations start to be washed out when we include in our sample more lower luminosity AGN. And we attribute these differences to the effects of AGN activity, and in particular, it could be that CO is excited, heated, or dissociated by the strong AGN radiation field. And we have a very interesting example in the local universe presented by Rosario and collaborators, where they observed a Seyfert galaxy and mapped the CO emission here in yellow and orange, and they found a cavity of CO surrounding the central engine. However, this cavity of CO is actually filled with warm molecular and ionized gas. And this means that the gas is there, is just in a hotter status. In this case, the extent of this lacuna is a few hundred parsec. However, in our case, at high redshift, where AGN are more powerful, it could be that this lacuna effect is more extended. And therefore, this is why we could see, for example, a decrease in the CO luminosity of our targets. And the other option is that AGN-driven outflows affect the gas reservoir, as has been observed already in a few powerful AGN at high redshift. And so I want to conclude by changing slightly focus. So I told you at the beginning that integral field spectroscopy studies are necessary to understand the physics of AGN feedback, as they provide a detailed view on outflows. However, especially at high redshift, we are still limited in this kind of studies because they don't achieve the statistical extent to provide large samples that allow us to then derive scaling relations. So these scaling relations tell us, for example, how outflow properties such as the velocities vary as a function of AGN and galaxy properties. So for this, we still need spectroscopic surveys. And we have very interesting results, mainly from SDSS, so in the kind of more nearby universe up to redshift 0.4, from which we learned that outflows are more prevalent in AGN than in inactive galaxies, as you see here in this spectrum for star-forming galaxies and type 1 AGN, where we see these broad and blue-shifted components. But also, we learned that faster outflows develop in more powerful AGN, as you see here in this plot, with the turbulence of the gas as a function of AGN luminosity. So, as I said, the point here is that we get up to redshift 0.4. However, these scaling relations are also necessary as inputs for cosmological simulations, and therefore we need to go back in time up to at least cosmic noon, where we have the peak in galaxy and supermassive black hole growth. And so this is why we are trying to do with the dark energy spectroscopic instrument. This is a survey, an ongoing survey. I'll give you more details in a moment, which will collect in a few years a few million optical spectra of AGN. And the idea is to use this survey to identify outflows in oxygen-3 in AGN, and to use this statistical sample to derive outflow scaling relations that then can be used to test models of galaxy evolution. We can also determine the occurrence of outflows, so how often we find them in galaxies, up to redshift 1. And this will bridge the gap between the local universe, so with SDSS, and future surveys, for example, at the VLT or Subaru, focusing especially on cosmic noon. So a few pieces of information on DESI. This is an optical multifiber instrument installed at the 4-meter Mayal telescope at Kitt Peak in Arizona. It uses 5,000 fibers, so it takes 5,000 spectra at a time, split over 10 spectrographs. And it covers a wavelength range between 3,600 and 9,800 angstrom. And DESI observes 4 target classes at different redshift, as you see here in this plot at the bottom. So there are bright galaxies, red galaxies, emission line galaxies, and quasars. And there is a lot of ongoing work in the collaboration to try to extract all AGN from all the target classes, well, on top of quasars, of course, which are sort of the bright members of the family, also selected to be point-like and so on. But in the other target classes, there could be AGN that we are missing and that we are trying to identify by using multivalent tracers. And here in the top, in the plot at the top, you can see the distribution of this and the density of these targets in the sky. So the method that we are using to study outflows on a statistical basis is to subtract the continuum, which is derived with a code called FastSpecFit. This is a code developed on purpose for DESI and is performing a fit of the spectrum and the photometry as well. And once we are left only with our emission lines, we focus on the oxygen tree line and fit Gaussian components to identify any broad and or blue shifted emission in the emission line. And you can see an example here at the bottom. And so I'm going to show you some preliminary work. These are mainly tests that I've done on a few thousand AGN from the AGN catalog, just to give you an idea of what we can do with this kind of data sets. So here you see the redshift distribution for this subsample that I've analyzed. And we found that about 30% of the sources need a second component to best reproduce their emission line. In this broad component, we find mostly 50–60% of the flux. And we can, for example, analyze the velocity shift of the broad component with respect to the narrow line. And what you see here as a function of redshift is that this velocity shift on average is negative, so we have blue shifted emission in the line, and we can analyze. It is still early to take any conclusion, but for example, we may find faster outflows as a function of redshift, so a decrease in the velocity shift with redshift. Okay, so this brings me to my summary. I hope I convinced you that a multivalent approach is crucial to gain further knowledge on the role of AGN in galaxy evolution. We started with the ionized view, where we saw the outflows are ubiquitous in AGN at cosmic noon. With IFS data, we can constrain the morphology and the distribution of the outflow in the galaxy, but we still need spectroscopic surveys as a powerful tool to derive scaling relations over statistical samples. From the dusty view, we saw the impact of outflows, the instantaneous impact on star formation is quite elusive and difficult to constrain, maybe due to smaller physical scales or different time scales of the feedback. And finally, from the molecular view, we saw the AGN feature lower CO luminosities compared to inactive galaxies. However, the significance is quite low, and it becomes even lower when including kind of less luminous AGN. And we interpret this as a hint towards the effect of AGN activity. So that's it. Thank you very much for your attention.
Thank you very much, Chiara. Very interesting talk, very nice results. And we have time for some questions. You can unmute your microphone, do some. Well, in the meanwhile, I have some questions. I was impressed when you mentioned the typical size of the ionized component of the outflow component in the ionized phase. If I well remember, they can reach up to 6 kiloparsec in size. I was wondering if you have any evidence of the presence of any radiojet emission that could induce the presence of this ionized outflow.
Yes, that's a very good point. So in this specific sample, we don't have the resolution at the moment to, probe any morphology in radio. We have evidence from, just comparing radioluminosity with far-infrared luminosities that some AGN are so-called radio loud, so they may have jets, but we don't have the resolution to trace them so far. And but however, there are other surveys at lower redshift, for example, the quasar feedback survey, where, since it's nearby targets, there is the resolution to trace jets. And actually, yes, we observed that even compact jets may be connected with the production of these outflows. So yeah, but it's a very good point. It's something super interesting, but yeah, we need high resolution radio observations to trace them.
Thank you. So, any other questions? And
okay, Alex.
Hi, Patricia.
Chiara. Thank you for the talk. Yeah, very interesting. I was curious that when you saw the velocities of the carbon-4 and the correlation of the velocities of the two lines, the O3 and
yes,
carbon-4, there was, it's true that the correlation was good, but for some galaxies, there were substantial differences. And I was wondering if what is due to is the ionization structure of well, yeah, tell me, you tell me. Or no, I was wondering if we can learn something about by learning about the ionization structure of the outflow, we can learn something about also the size or the
yes. So I think that the main point for that plot is the following, this is that when looking at an outflow episode, for example, in the broadline region and in the narrowline region, on a kind of time scale, let's say scenario, it's not the same outflow episode. Because of course the outflow that got to the narrowline region was produced before what we are currently seeing in the broadline region. So I think that some of the scatter may be due, for example, to this factor that is basically two feedback, like two outflow episodes. Then on the ionization and the structure, I don't know, because for example in the oxygen 3, we can still map the distribution of the outflow, but in carbon 4, for example, it's just kind of one spectrum for the whole galaxy. So we don't have spatial information. Maybe with for example, with this different normalization of the two correlations, we could learn something on the physical properties of the ISM, but I would say that probably still a bit difficult, especially with the small samples that we have here.
Okay, thank you. Well, also, how people sorry, I don't know whether it's
no.
Yeah, no, please go ahead. Also, if you have any suggestions.
No, I was wondering also if there is if you could also I was trying to see how. Yeah, I don't know. I was trying to see how, but maybe you can. Yeah. No, I was trying to see how can you combine the molecular gas information and the ionized gas information, no? Yeah. Also to learn something about the structure. To learn also. But no, I was gonna ask if someone has done something, but I was thinking that cannot be done. So. Sorry. Question.
Yeah, probably maybe I can add here. So for the molecular phase, we just can probe with these observations the kind of just the molecular gas reservoir and not outflows, because we don't have enough signals. So, or anyway, with the observations we don't see any.
That's what I figured out. That's why, I was going to ask you about the correlation between the velocity.
Yeah, no, in that case, it would be just the molecular.
You can only measure mass, okay.
Yeah.
And is there some of these? No, I don't know. And the maximum size, more or less, that you found is like 4 kiloparsecs or 5 kiloparsecs.
Yeah, it's 6, and in some cases, like in most of the cases, actually unresolved, so it's more compact than our 2-3 kiloparsecs resolution. Yeah.
And having into account that the resolution of the DESI spectra is, I don't remember, around 3,000 or something like that. The resolution.
Yes, well, but so the kind of spatially resolved studies are with SINFONI, but with DESI we don't have this kind of.
Yeah, I know, but I was wondering what
Yeah.
is the, I mean, because you say that you find like a float in about 30% or something like that.
Yes, yeah.
And I was wondering, like, given the resolution, you can extrapolate that. I mean, because I guess there are some outputs that you are not resolving the two lines because of the resolution, which is, so I was wondering if that can be extrapolated to get an estimate of the total.
Yeah, well, the problem with the spectra that we get from DESI is mostly the signal to noise that quite often doesn't allow us to see this broad component because it's faint, so you need a good signal to noise. But being a cosmological survey, then the main information that we need to extract is the redshift, and then, well, we are using also the spectra for galaxy evolution studies, but I would say the main limitation here may be the signal to noise. Still, I'm still investigating, I don't know, finishing the fits of the sample, but it could be probably the signal to noise. Yeah.
Thank you.
So, any other questions? Well, I have another one, just a curiosity. Do you have any information about the metallicity in your sample? If you found, for example, any metallicity gradient?
So, well, no, we don't have information because I'm not expert on metallicity studies, but I think that the main lines used for metallicity in this case are contaminated by the AGN. So I think it would be difficult in this sense to derive.
But if you can model the different components, maybe. No, well, I mean, you can measure metallicity with the AGN. I mean, with you use photoionization models that are with the ionized with a source like an AGN, like with a harder radiation. You in principle could derive.
Yeah, well, we don't have all the lines, I think, but this is something we can think about. Yeah.
But in Muse, you have used Muse. You have the whole Muse spectrum.
Sorry, you have?
You've saw like observations with Muse and with SINFONI, and the wavelength range there is
yeah, we just have SINFONI for now, but yeah, in principle we will need to extend the wavelength range. Yeah.
Okay. So I think if there are no more questions, let's
the last one.
Yeah, the last one. Okay.
When you look for the spatial correlation between the star formation and outflows, I don't know if you. I was wondering what is the effect of the projection effects, because you I guess unless you expect a star formation in the outflows itself, maybe the correlation is simply because.
So you mean the spatial anti-correlation between outflow and
the spatial correlation between the star formation region.
Yeah, so I think that's I didn't highlight it then when I showed the dust continuum results, but that's a bit debated because in some cases the H alpha was used to trace star formation, but it's contaminated by the AGN, so it's not always very reliable. And also there may be some obscuration effect because, for example, if there is dust, H alpha may be obscured. So it's these are quite debated. And also there is also the problem that it's all projected, and therefore you try
that was my question, basically, that with the projection effect, it will depend.
Yeah, but it's still true that in some cases this anti-correlation is there. So
yeah, you have the optimal inclination, maybe. I
Yeah.
mean, the fact that you find in some case, I mean, can be a question of time scale, no? But also can be, I guess, I think, I don't know, if I'm not an expert, I think.
Yeah, no, it's true. Yes.
No, it's very interesting. Thank you. Nobody else want to make a question?
So if there are no more questions, I think we can stop here. And let's thank Chiara again. Thank you very much, Chiara.
Thank you very much for the invitation. It was a pleasure.
For you, for me
Thank
too.
you.
Thank you. So goodbye. Thank you everyone for joining us.
Bye-bye.
Thank you. Bye.